So in this video I'm going to explain second PU physics nuclear physics chapter. So this is the part 2 video. So in my first part I explained neutron, nucleus, mass effect and binding energy curve and nuclear reaction. Now I'm going to discuss from nuclear fission and fusion. So let us come to the topic nuclear fission and fusion. Yes, so nuclear fission and fusion. So nuclear fission. So it is the process of splitting of an heavy nucleus into two lighter nuclei. So nuclear fission, it is a process in which two heavy nuclei is split into two lighter nuclei of comparable mass. Means the lighter nuclei, it has same mass with liberation of energy is called nuclear fission. So the process of splitting of heavy nucleus into two lighter nucleus of comparable mass and with the liberation of some energy is called nuclear fission. So one heavy nuclei, it is divided into two lighter nuclei that are having same mass with some energy is released when the heavy nuclear is separated. It becomes a lighter nuclei. It means two lighter nuclei. That is called as a nuclear fission. So this nuclear fission was discovered by the scientist Otto Hahn and F. Strassmann, and it was explained by N. Bohr and J. A. Wheeler on the basis of the liquid drop model of nucleus. So fission reaction of U-235. Nuclear reaction is U-23592. So this is the nuclear reaction. The energy released in U-235 fission is about 200 MeV or 0.8 MeV per nucleon. By fission of U-235, on an average 2.5 neutron are liberated. So on an average 2.5 neutrons are get liberated. These neutrons that get liberated are called as fast neutrons, and their energy is about 2 MeV for each neutron. Next is fusion of U-235 occurs by slow neutron only or even by thermal neutron. So fusion of U-235 occurs by slow neutron that have energy above 1 eV and or even thermal neutron that have energy of about 0.025 eV. And the mass of compound nucleus must be greater than the sum of the mass of fission product. So the mass of the compound nucleus, it should be greater than the sum of the masses of their fission product. The binding energy by A of compound nucleus must be less than that of the fission product. So the binding energy A by A of compound nucleus must be lesser than that of the fission product. So it may be pointed out that it is not necessary that in each fusion of uranium, the two fragments in each fusion of uranium, two fragments like Ba and Kr are formed, but there may be any stable isotopes of middleweight atoms. This is so. So it is not necessary that when each fusion of uranium occurs, two things B and Kr are formed. B and Kr will be formed. It is not necessary. It may be formed sometimes, but there may be any stable isotopes of middleweight atoms. So there may be any stable isotopes that have equal number of weightage atoms. So the neutrons released during this fusion process, when the neutron released, it is called as prompt neutron. Most of energy released appears in the appears in the form of kinetic energy of fission fragment. So this is the kinetic energy of fission fragment. So this was the first thing, that is fission reaction of uranium 235. Next is chain reaction. So in nuclear fission, three neutrons are produced. In nuclear fission, three neutrons are produced along with the release of large energy. So three neutrons means in nuclear fission there are three neutrons are produced, along with which the release of large energy. Large energy is also released with that three neutrons that are produced. Under some conditions, these neutrons it can be used for more forward fission of other nucleus. So these nucleus, three nuclear neutrons that we get, it can be used further for more other nuclear fusion also, that produces a large number, with that makes large number of neutrons will be produced, by which thus a chain of nuclear fission is established. So there will be a chain of nuclear fusion. As three neutrons is produced, that three neutrons will produce more neutrons. Like this chain will be produced. Chain will be there. So like this chain will be there. That uranium chain, in this chain reaction, the number of nuclei undergoing fission increases very fast. So in this chain reaction, the number of nuclei, the nucleus that are undergoing fission reaction, it increases. It will be increasing very fast. So the energy produced takes a tremendous magnitude very soon. So the energy that is produced, it takes a tremendous magnitude, it is very fast. So what are the difficulties that we get in chain reaction is absorption of neutron by uranium 238. So the major part of the natural uranium is the isotope that it has, that is uranium 238. That is 99.3% of the uranium 238 is present in this chain reaction. The isotopes U235 means uranium 235 is very little, that is 0.7 is the isotopes of U235 is there, uranium 235. It is found that uranium 238 is fissionable with the fast neutron. So it is found that uranium 238 is fissionable with the fast neutron, whereas uranium 235 is fissionable with slow neutrons. So due to large percent of uranium 238, there is more possible of collision of neutrons with uranium 238. So therefore it is found that the neutrons get slowed on colliding with uranium 238. As a result of this, further fusion of uranium 238 will be not be possible. So therefore this stops the chain reaction. The chain reaction will be stopped by this. Next difficulty is if neutron are slowed down. If neutron gets slowed down by any method to an energy of about 0.3 eV, then the probability of their absorption by uranium 238 becomes very slow, while the probability of their fissioning with uranium 235 will become high. This job is done by moderator, which reduces the speed of neutron rapidly. Graphite and heavy water are some of the examples for moderator. Next is critical size. The neutrons emitted during fission are very fast. The nuclei that we emitted during fission, it is very fast, and they travel a large distance before being slowed down. Before being slowed down, they travel a very large amount of distance. And if the size of the fissionable material, if the size of them is small, then the neutrons emitted will escape the fissionable material before they are slowed down. Hence, the chain reaction cannot be sustained. Hence, the chain reaction it will be not sustained. Okay. Next, there are different types of chain reaction. The chain reaction are like this: controlled chain reaction, controlled by artificial method, and uncontrolled chain reaction. No control over this type of nuclear reaction. There is no control, and all neurons are absorbed except one in the controlled chain reaction. Here, in the uncontrolled chain reaction, more than one neutron takes part into the reaction. And in controlled chain reaction, its rate is slow. In uncontrolled, it is very much fast. The reproduction factor K is equal to 1. So reproduction factor is K is small the greater than 1. Energy liberated is in this type of reaction is always less than the explosive energy in the controlled chain reaction, whereas in uncontrolled chain reaction, a large amount of energy is liberated in this type of reactions. Chain reaction, it is the principle of this nuclear reactor in the controlled chain reaction. Uncontrolled chain reaction is the principle of the atom bomb. So this is the difference between controlled reaction and uncontrolled reaction. Next is nuclear reactor. So the nuclear reactor, it is the device in which the nuclear fission can be carried out through a sustained and a controlled chain reaction. So it is a device in which the reaction is nuclear fission can be carried out through a sustained and a controlled chain reaction. Through a sustained chain controlled reaction, the nuclear fission reaction can be carried out in this nuclear reactor, and this is also called as atomic pile. It is thus a source of controlled energy which is utilized for many useful purposes. For many useful purposes, this nuclear reactor is utilized. So here you can see the diagram of nuclear reactor. So it has coolant, concrete wall, moderator. It has, as I said, graphite and water or moderator for them. So fuel elements and coolant in heat exchanger, water condenser to electric generator, the turbine, coolant out, core, and this is the cadmium rods. So these are the things that are there in the nuclear reactor. Now let us learn about that part one by one in the parts of nuclear reactor. Fissionable material, that is fuel. So the fissionable material that is used in the nuclear reactor is called as the fuel of the reactor. Uranium isotope, that is U-235, and thorium isotope TH-232, and plutonium isotope Pu-235, Pu-240, and Pu-241. These are the most commonly used fuels in the nuclear reactor. Then the next is moderator. Moderator, it is used to slow down the fast moving neutrons. It helps to slow down the fast moving neutrons. Most commonly used moderator, as I said, they are the heavy water and graphite. And next is control material. So control material, it is used to control this chain reaction, and also it helps to maintain a stable rate of reaction. So it helps to maintain a stable rate of reaction and helps to control the chain reaction. This material controls the number of neutrons. This material means that is control material. It helps to control the number of neutrons that are available for this fission. Next is coolant. Coolant is a cooling material which removes the heat generated due to fission in the reactor. So coolant, it is a cooling material that removes the heat that is generated due to fission in that reactor. Protective shield. So a protective shield in the form of concrete thick wall surrounds the core of the reactor so that it can save the person working around the reactor from the hazards or the hazards that are caused sometimes if a reaction gets wrong. Next, where we can use this nuclear reactor. So in electric power generator it can be used, and also it can be used to produce radioactive isotopes for their use in the medical science, agriculture and industry, and in a manufacture of PO235 and 239 element which is used for atom bomb, and they are used to produce neutron beam of high intensity which is used in the treatment of cancer and nuclear research. Next is nuclear fusion. In nuclear fusion, two or more than two lighter nuclei combine to form a single heavy nucleus. So in nuclear fission, there was a heavy nuclei. It is divided into two lighter nuclei, right? But here in nuclear fusion, two or more lighter nuclei combines to form a single heavy nuclei. So the mass of single nuclei is formed, it will be less than the sum of the mass of the parent nuclei. So the mass of parent nuclei is more when we compare to the mass of the nuclei. So here is the reaction they have given. Next, in fusion energy is greater than the fusion energy is greater than the fission energy. Fusion of one uranium atom releases about 200 MeV of energy, but the fusion of deuteron, that is H2 and triton H3, releases only 17.6 MeV of energy. So therefore, fusion energy is greater when we compare with fission energy. Next is plasma. So plasma, it is the temperature of the order of 108 Kelvin required for thermonuclear reactions. That is lead to the complete ionization of the atom of light element. So the combination of base nuclei and the electron cloud is called as the plasma. So the combination of a small nuclei, base nuclei, and electron cloud is called as the plasma. The main problem to carry out nuclear fusion in the laboratory is to contain the plasma at the temperature of 108 Kelvin. No solid container can tolerate this much temperature. If this problem of containing plasma is solved, then the large quantity of deuterium present in seawater would be able to serve as in the exhaustible source of energy. So it will be, if this problem of plasma, that is 108 Kelvin should be the temperature, if it is solved, then we can use the C as also the electron current producing, so a source of producing energy they are telling. Next is stellar energy. Stellar energy is the energy that is obtained continuously from the sun and the stars. So it is the energy that we obtain from sun and the stars. Sun radiates energy at the rate of about 1026 joules per second. So sun, it emits an energy that is 1026 joule per second amount of energy is emitted by sun. The scientist, that is Hans Bethe, suggested that the fusion of hydrogen to form helium is continuously taking place in the sun, and it is the source of sun's and stars energy also. The stellar energy is explained by two cycles, that is from proton-proton cycle and carbon-nitrogen cycle. So this is the proton cycle, you can see, and there is a difference between both proton-proton cycle and carbon-nitrogen cycle also. So about 90% of the mass of sun consists of hydrogen and helium. So therefore, you can see more number of energy is emitted by the sun, and also stars also some energy is emitted. Next is nuclear bomb. So based on uncontrolled nuclear reaction, atom bomb and hydrogen bomb, it is divided. Atom bomb, based on the fission process, it involves the fission of uranium 235. But hydrogen bomb, it is based on fusion process, that is mixture of deuteron and tritium is used in it. So both are differences there. In this atom bomb, you use the fusion of uranium 235, but here in the hydrogen bomb, you use it is a mixture of deuteron and tritium element. So in this, critical size is important in the atom bomb, but in the hydrogen bomb there is no limit of to be critical size. In atom bomb, explosion is possible at normal temperature and pressure, but in hydrogen bomb, high temperature and pressure are required for it. In atom bomb, less energy is released compared to hydrogen bomb, but hydrogen bomb, more energy is released as compared to atom bomb. Uh, hydrogen energy, it is more dangerous than the atom bomb. So here they have given a basic concept. There is a test tube full of base nuclei will weight heavier than the Earth. The nucleus of the hydrogen contains only one proton. Therefore, we may say that the proton is the nucleus of the hydrogen atom. The next topic is radioactivity. So in this, radioactivity, It is radioactivity. It is the phenomena of spontaneous emission of radiations by heavy material or heavy element. So it is the phenomena in which spontaneous emission of radiation is taken place by heavy elements. The elements which show this phenomena is called the elements that show this radioactive phenomena is called as radioactive element. So radioactivity was discovered by scientist Henry Becquerel in uranium salt in the year 1896. After the discovery of radioactivity in uranium, Pierre Curie, Pierre Curie and Madame Curie discovered a radioactive element that is called radium, which is 106 times more radioactive than the uranium. Some examples of radioactive substances are uranium, radium, thorium, polonium, and neptunium, and many more are there. Radioactivity of a sample cannot be controlled by any physical, that is means the radioactivity of a sample, it cannot be controlled by any physical, that is pressure, temperature, electric or magnetic field, or any chemical change, it cannot be controlled. All the elements with atomic number Z is greater than 82 are naturally radioactive. The conversion of lighter element into radioactive element by the bombardment of fast moving particles is called artificial or induced radioactivity. Radioactivity of is a nuclear event and not atomic, so hence electronic configuration of atom don't have any relationship with this radioactive activity concept. So nuclear radiation. So in this, according to the scientist Rutherford's experiment, when a sample of radioactive substance is put in lead box and allow the emission of radiation through a small hole only, when the radiation enters into the external electric field, the element is split into three parts. So next, that is the radiation which deflects towards negative plate, they are called as arrays. Stream of positively charged particles. Radiation which deflects towards positive plate, they are called as p particles. They are stream of negative charged particles. Radiation which are undeflected, they are called as wire em waves or photons. Next is properties of a, b and wire. So identity of a ray: helium nucleus, alpha, beta, and gamma ray. Helium nucleus or doubly ionized helium atoms, fast moving electrons, beta ray, and gamma ray photons, EMB. Charges is plus 2e for a alpha particle, beta particles minus e, and 0 for gamma particles. Mass 4 mp, so 4 mp for alpha particles, e for beta particles, and massless gamma particles. Speed is concurrent to 107 meter per second for alpha particles and 1% to 99% of speed of light beta particles, and speed of light is for gamma particles. Range of kinetic energy 4 MeV, 4 MeV to 9 MeV for alpha particle. All possible values between a minimum certain value to 1.2 MeV is for beta particle, and between a minimum value or value to 2.23 MeV is for gamma particle. Next, penetration power, that is 1 is for alpha particle, that is stopped by a paper. 100 is for beta particle, 100 times of A, and 10,000 is for gamma particle, that is 100 times of B up to 30 centimeter of iron or PB sheet. Ionization power is 10,000 for alpha particle and 100 for beta particle and 1 for gamma particle. Effect of electric or magnetic field. So deflected for alpha and beta particle and not deflected for gamma particle. Energy spectrum, line and discrete for alpha particle, continuous for beta particle, and line and discrete for gamma, gamma particle. And mutual interaction with matter produces heat. It produces heat for both alpha and beta particles. It produces photoelectric effect, Compton effect, pair protection. So equation of decay you can see here. Next is radioactive disintegration. So law of radioactive disintegration. So according to Rutherford and Suri's law for radioactive decay, at any instant of rate of decay of radioactive atom is proportional to the number of atoms that are present at that time. This is the formula. So it can be proved that N is equal to N naught E valent T. This equation can be also written in the terms of M is equal to M naught E is equal to valent T. Here N is the number of atoms remains undecaying after time T. NO or N0 is the number of atoms present initially. M is the mass of radioactive nuclei at that time, and MO or M0 is the mass of radioactive nuclei at that time. T is equal to 0. NO minus N is equal to number of disintegrated nucleus in the time T. So 1 minute. Okay, so dN by dt is equal to rate of decay. Wavelength is the decay constant or disintegration constant or radioactivity constant. Many types of name is there for this. Next is they have given here an activity, so it can be done by yourself. Next is half time, that is T1 by 2 also we can say. So the time interval in which the mass of radioactive substance or the number of its atom reduces to half of its initial value. So the time interval in which the mass of the radioactive substance or the number of its atom it gets reduced to half of its initial value, it is called as the half life of a substance. If n is equal to n naught by 2, then t is equal to capital T 1 by 2. Hence, from n is equal to n naught e to the power minus wavelength t. N naught by 2 is equal to n naught e to the power minus wavelength t1 by 2. So, this is the formula. Finally, t1 by 2 is equal to log e2 by wavelength, that is equal to 0.693 by 0.693 by wavelength. So, time, number of undecayed atoms, remaining fraction of active atoms, fraction of atoms decay n naught minus n, no probability of decay. So for t is equal to 0, so there will be no only, so no number of initial atoms. Here remaining fractions of active atoms only 1, fraction of atom decayed is 0. For t is equal to t1 by 2, n naught by 2 is for number of undecayed atom. For remaining fraction of active atoms 1 by 2, that is 50%. Fraction of atom decayed is 1 by 2 for n naught minus n, so it is also 50%. Next is T is equal to 2 into T1 by 2. That is 1 by 2 into N naught by 2, that is equal to N naught by 2 whole square. And for remaining fraction of active atoms is 1 by 4, that is 25%. 3 by 4, that is 75%. So only I think this is important so that you can see it, you can read it by yourself. Next is mean or average life. So the time for which a radioactive material remains active is defined as mean or average life of that material. Other definitions are it may be like it is defined as the sum of the lives of all atoms divided by the total number of the atoms we have. This is the formula we can take. So about that only. Next is radioactive series. That is, if the isotope that results from a radioactive decay is itself radioactive, then it will also decay and so on. So, if the isotope that results from radioactive decay, the isotope it results from radioactive decay, it is a radioactive, then it will also get decay and it will go on. The sequence of decay is also known as radioactive decay series. It gets on decaying, decay means it gets on dying. Most of the radionuclides found in nature and members of four radioactive series are like this. Mass number that is 4n, 4n plus 1, 4n plus 2, 4n plus 3. So for series that is 4n, it is thorium, that is natural. Parent is TH232 by 890 underscore. Stable and product is 82 PV208. So integer n is 52. The number of lost particle is alpha 6 beta 4. For 4n plus 1 that is neptunium, it is Np237 is the formula, Bn209. So 52 integer n, alpha is equal to 8, beta is equal to 5. 4n plus 2 uranium natural, it is uranium 238 Pb206, 51 element integer n is there, A is equal to 8, alpha beta is equal to 6. Then 4n plus 3 actinium natural, it is actinium 227 89 Pb207, so it is 51 integer n is 51, so A is equal to 7, alpha beta is equal to 4. The final topic of this nuclear physics chapter is successive disintegration and radioactive equilibrium. Suppose a radioactive element A, it disintegrates to form another radioactive element B, which in turn disintegrates to still another element, that is C. Such decay are called successive disintegration. Suppose let us take a radioactive element. It is A. It disintegrates so that it can form another radioactive element. So it disintegrates so that it can form another radioactive element, that is P, which inter disintegrates to still another element. So it again disintegrates to another element and forms C. Such decays that gets disintegrated for 2 or 3 times, it is called as successive disintegration. See here only they are given A to B to C like this. Radioactive disintegration of A is equal to dN1 by dt, that is equal to minus N1 by N1. B is also is equal to dN2 by dt, that is equal to alpha minus wavelength 2 into N2. Next is equilibrium. So in radioactive equilibrium, the rate of decay of any radioactive product is just equal to its rate of production from the previous member. That is wavelength 1 N1 is equal to wavelength 2 N2. That is equal to wavelength 1 by wavelength 2, that is equal to N2 by N2, that is equal to by 2 by 1. So therefore it is equal to T1 by 2 by T1 by 2 into 1. Next, use of radioactive isotopes, where it is used in medicines for testing blood chromium 51, for testing blood circulation Na24, for detecting brain tumor radiomercury 203, for detecting fault in thyroid gland radioiodine 131, and for cancer cobalt 60, and for blood gold, that is gold, 189, and for skin diseases phosphorus 31. And in archaeology, for determining the age of archaeological samples, carbon dating for the C14, and for determining the age of meteorites, that is K40, for determining the age of earth lead isotopes. In agriculture, it is used for uh, protecting potato crop from earthworms CO60, and for artificial rains AGI, and for as for fertilizers, that is P32. As trackers, very small quantity of radio sorry radioisotopes are present in the mixture is known as the tracer. So a very small quantity of radioisotopes are present, that is in a mixture is known as the tracer. Tracer technique is used for studying biochemical reactions in tracer and animals. In industries, for detecting leakage in oil or water pipeline, for determining the age of planets. For this, the radioactive is used. Radioactive isotopes is used for these things. So finally, our concept is the nuclide can decay simultaneously by two different processes which have decay constant wavelength 1 and wavelength 2, half-life T1 and T2, and mean live P1 and P2 respectively. Then so here also you can see formula, that is mu, that is mu1 by mu2, mu1 plus mu2. So therefore this was your chapter, that is nuclear physics. So okay friends, I have completed all the topics of this chapter. So I believe you understand what all the topics, important topics are there in this chapter. So I will see you in my next video with some other topics. And then take care, have a nice day, bye my dear friends.